This talk is about optimizing data analytics in the cloud, and this joint work with Dimitrios, Orion, Dushyanth, Florin, and Antony. Traditional data analytics platforms, such as Hadoop, are built by using a cluster of nodes that combine both storage and compute. However, there is a new breed in data analytics that use cloud services. For example, you could use Azure Storage to store your data and Azure Compute to do your computation. Systems like Hadoop on Azure and Amazon's Elastic MapReduce are examples in this category. What is really interesting in those systems is the separation between storage and compute. And this is important for many reasons. The users now don't need to pay for compute only to keep their data alive. Also, they don't need to manage the storage for reliability, scalability, and performance. They offload the operation to the operator. From the operator's point of view, the separation also allows them to evolve the two infrastructures independently. Also, often they offer other services on top of them that don't really combine both. However, there is a disadvantage. Now, data have to go from storage to compute over a piece of the infrastructure that it is precious and bottlenecked. Right? We have done some measurements in the papers where we try to characterize that the capacity of that infrastructure, and we found it to be in the order of a few hundreds of megabytes per second per node in the best of the cases. Please see the paper for more details. So what the jobs are doing in that new setting is that, assuming that you have some big amount of data in the storage, you have to send it over this network to the compute nodes, and then you do the computation. Now, the key insight that motivated our work was that quite often, the jobs that operate on the data are really interested in a subset of the data. Assuming that you view your data in a tabular form, the job may be interested only on a subset of the rows, and on those rows, they may only be interested on the subset of columns. So the problem, again, is that we have to send a lot of data from storage to compute only to operate only on a subset of those data. Right. So to summarize, basically, our setting is that we try to work on Hadoop on Azure, that run as a cloud service. Our input data are in a storage node, and we run Hadoop in a compute service. As is quite common in those cases, the input data are in a textual form, and for example, they can be log files or whatever. And our goal is to transparently reduce the data transfers from storage to compute. The Strongman approach to solve this problem is to basically move the execution of the mappers to the storage nodes. However, that has a number of problems. First of all, it doesn't often always guarantee that the number of bytes transferred will be reduced. The more important shortcoming of this approach, though, is that now we have to run the full Hadoop protocol at the storage infrastructure. That basically means that if and when the storage nodes get overloaded, we will not be able to, for example, kill those mappers, because now the performance will get really degraded. So instead, the approach that we advocate here is the following. We want to generate lightweight filters and then use them to filter unnecessary data at the storage nodes. Our filters need to be opportunistic and transparent. That basically means that the storage infrastructure should be able to kill and restart them at arbitrary points in time without affecting the computation. Moreover, they need to be correct. That basically means that we have to get the same result at the end as if the job was running on the original unstructured data. So how can we do this filtering? The problem is difficult because the data are basically unstructured, and we don't really have any information about, say, their schema or other properties of them. The insight that we have in this work is the following, that there is that information, but it is hidden inside the job. The job knows what the structure looks like and also what is needed. All right. Let's take an example of a very simple job to understand how this structure is hidden. In this listing, I have a very simple mapper. It is written in Java, and it is a bit listing, so bear with me for a bit to give you the important things. There is the input comes as an argument of the method. And then the very last instruction in this listing is basically where the job is writing data for further processing. Somewhere in the middle of the listing, there is a conditional. That conditional basically says that not all inputs lead to output. Indeed, in this particular example, only 1/3 of the inputs will actually satisfy the conditional, and output will be produced. This can be thought of as a select operation in a database world. The first part of the method is also interesting. Observe here that the mapper tokenizes the data and uses 3 out of 4 of the columns of each row. So this can be thought of as a projection operation. So these select and project operations are indeed exist inside the code of the mapper, but they are implicit, and we have to extract them. This is exactly what Rhea is doing. With Rhea, we perform static analysis on the job's bytecode, and we want to extract row and column filters. These filters are executable Java methods, even though for column filters, we have managed to generate optimized C, and we can also run it as regular expressions and so on. And they have a number of properties. They are conservative. That means that sometimes we are not able to precisely identify only the data of interest to the job. We may have to send some more data. They are also opportunistic. That basically means that the storage nodes can kill and restart them at arbitrary points in time. And as they are transparent, which means that we don't really change the Hadoop jobs. They are executed as before in the compute cloud infrastructure. So this is a brief outline of how we have implemented the system. When a job gets submitted, it goes through the filter extraction engine that analyzes all mappers and generates for each of them filters and uploads them to close to the storage nodes. We also perform a very slight modification to the job to guarantee that the job requests the input data through the filter engine and not directly from the storage nodes. And when the job runs, the data come from storage, they get filtered, and only the subset of interest goes through the network to the compute nodes. So in the rest of the talk, I will describe how we have implemented those filters and what performance we can get. Now, filters, as I mentioned before, do the following. We want to identify the bits of data that are of interest to the job, and we do it as follows. We first construct row filters. A row, in this case, is an invocation of the input of the invocation of the mapper. So the row filter identifies the rows that may generate output data. For each row that is of interest, we then apply the column filter that tells us which subset, which substrings of that row are of interest to that job. Now, how do we generate those row filters? Again, this is the listing that I showed you before, and our approach works as follows. We first identify the output instructions. In this particular case, it is the very last instruction in the end. We call these output instructions observable instructions. Then we identify all paths from the entrance of the job to all observable instructions, and we identify the conditionals along those paths. The next step is to perform data flow analysis to identify all instructions that are necessary to compute those conditionals. And we collect both the conditionals and those instructions and create the output filter. For example, in this case, the filter contains the if conditional plus all instructions necessary to compute it. If MapReduce programs mappers were always pure, as this is encouraged by the MapReduce framework, our job would be done. However, this is seldom the case in practice. Quite a few mappers use state for many reasons, often to improve performance. So filters, on the other hand, cannot really rely on impurities, on mutable state. And the reason is that we should be able to stop and restart them arbitrarily. So the solution that we adopt in this approach is the following. We analyze the code and we identify all instructions that either read or write to mutable state. And we tag those instructions as mutable as well. So when we perform the analysis, we'll say that an input is of interest if it writes something to output or if it reads or writes to mutable state. Now, coming back to the question of how we generate column filters, our approach is the following. We first identify, using some pattern identification of the code, the method by which the code tokenizes inputs. And then we use abstract interpretation to go through the code to identify all uses of those tokens. We collect them, and in this case, the collection is a set of numerical constraints that may say, for example, that tokens 3, 5, and from token 10 onwards are of interest, and then we output them. Observe here that we have to give constraints because we also have to deal with consumption of tokens in loops. See the paper for more details about that. So the output is a description of the tokenization method, along with parameters that are necessary to do it, for example, the separator character, as well as a list of the indices of interest. So this kind of summarizes the creation of filters. Let's see now whether we can get any performance out of using it. And in order to do that, we have done a number of experiments in which we used Hadoop, mostly Hadoop on Azure. Our input data were stored in Azure Storage, and the compute used Azure Compute. In this talk, I will describe the results of experiments on 8 jobs for which we had both the code and the data. In the paper, we have some further experiments with 200 jobs in which we analyze the properties of filter extraction, but I will not go into the detail. Moreover, in the following, I will concentrate on the case of having data in the same data center. We have some scenarios of jobs that run across data centers in the paper. The first question of interest is trying to identify the potential benefits of filtering, and we characterize them through a metric that we call selectivity. Selectivity is the ratio of the number of bytes of interest to the job over the total amount of bytes of the job. Obviously, low selectivity is better for us. Less data will have to go through the network. Right, so for the set of 8 jobs that we have experimented with, the selectivity is quite high. Then the next question is, where does this selectivity come from? So in this particular case, we want to question, is it coming from actually performing row filtering or column filtering? The other 2 plots, they have these numbers for row filtering and column filtering only. And what we observe is that some jobs are very selective with respect to rows, some others are very selective with respect to columns, and some on both. So in summary, we need both row filtering and column filtering to reap the maximum benefits of Rhea. So when we have high selectivity, we send less data from storage to compute, and this is good for multiple reasons. It is good for the operators because we put less load on the network that connects them. It is also cheaper for users when the data have to traverse the boundaries of data centers. So in the paper, we have an experiment in which we process data in Europe and the original data are stored in the US. But another very important characteristic that we want to answer is whether it also reduces the runtime as perceived by the users. And this is what I will try to explain in the rest of the talk. Unfortunately, for us, we are not able to precisely and accurately measure that because we cannot really implement Rhea filters on either Azure Storage or Amazon's S3. So instead, we have done the following experiment. We used Rhea to pre-filter the data, and then we performed experiments using both filtered data and unfiltered data to compare. This comparison is meaningful under 2 key assumptions. First of all, that the storage subsystem is good enough and it has scalable I/O so that we can read data as fast as necessary. And also that there is enough processing power in the storage to actually execute the filters. For the first assumption, we expect to be true because this is the whole purpose for designing these storage infrastructures. Before I give you the results of the runtime benefits, I will actually concentrate on the second assumption. So for the jobs that we had available and the data, we have measured that the rate of process of performing row and column filtering in Java is around 100 megabytes per second per core. The important thing to observe here is that this is actually linear, the performance is linear with the number of cores. So increasing the number of cores, performance increases linearly. So given those numbers and the results that we get out for running the jobs, we have observed that up to 2 cores would have been enough to filter, to get the vast majority of, to get all the benefits of runtime filtering. Even if we had fewer cores than that, we will still get some runtime benefits, but it wouldn't be to the fullest extent. Actually, what we have also seen is that this limit of 2 cores for filtering is this number of 2 cores are enough for most of the jobs. Does not apply for one particular job that has been very selective. For that job, we would need up to 10 cores to get the full benefit of filtering. We have also observed that the performance of filtering is currently dominated by doing some string manipulations. and not really for running the filtering code itself. And our C-optimized column filtering method can give us much faster performance, 5 to 17 times faster than Java. So I'm coming back to the question that we wanted to answer, whether Rhea can give us benefits with respect to runtime. We observed that for our 8 jobs, we can see 30 to 80% performance in runtime. This basically means that the jobs that use filtered data run 30 to 80% faster than jobs that operate on unfiltered data. Observe that this particular number is smaller than the selectivity numbers that I have shown you a few slides earlier. And the reason is that due to some Hadoop overheads and also due to the fact that the job does more things than just filtering data. So to summarize, this talk started in the area of Hadoop in the cloud. And the fundamental assumption that we had is that there is a separation of storage and compute in that particular setting. We have designed Rhea to try to minimize the transfers from storage to compute. Rhea uses static analysis to extract, select, and project filters, and then those filters, which are lightweight, run together with the storage nodes to reduce the amount of bytes transferred before they hit the network that connects storage and compute. The filters are basically safe for the operator, and they also they are transparent to the user. We have also shown that they give performance benefits both to the operator and to the user. So thanks a lot for your attention. If you have any questions.
Hello, it's Ryan McElroy from Facebook. I was wondering if you have tested these filters directly, even in the situation where the storage is co-located with the compute, and if they have any benefits there or not.
So what we have done, which is not really, if I understood the question correctly, what we have done, which is not covered in the paper, we have actually set up in our local testbed kind of a simulation of a storage system, and we had also some compute nodes, and to run filters, run Rhea in that setting as well, and we did observe benefits. But this is not really covered in the paper. So if you want some more information, just find me in the break. Yes, go ahead.
While I'm waiting for some other people to ask some questions, one thing that I found kind of interesting about this work was that you were able to, without requiring source code access, you could, at least in the application of Hadoop and MapReduce and map jobs with Java, kind of do some of the selectivity. But it seems like people are generalizing beyond the map and reduce API to support things like SQL and Pig, or even if you look at work like Spark, which uses kind of declarative Scala type languages. I mean, do you think that some of these declarative languages could help here, or how would those work? Like, how would this generalize to systems beyond programming at that layer?
Right. Okay, let me actually clarify a bit of the question to give a bit more context. In some declarative settings, let's say the select and projects often are kind of explicit in the code that is given the user. However, even in those settings, the use of things like user-defined functions, especially to read data from disk and then transform it before further processing, is quite common. So in those cases, you will need to do some static analysis on the UDFs themselves. So we believe that it is applicable in that case as well, but it is not really also covered in this work. So here we focus mostly on Java. Okay, thanks.